Oh, it's 2:40, so we can get started. Let's see how many people we have here. 24. Seems more and more people are choosing to go asynchronous the farther we go into the semester. Not sure why that is, but it's the same in the other section too. Anyway, couple of announcements, same announcements as last time. Homework 6 is due on Monday. I think I'll be able to get through everything with the Earth and the Moon by the end of class Friday. We'll see. But so far, it's still the plan for Monday for when the homework's due. And the exam will be due, the exam will be available a week from Friday. And you'll have 24 hours. And we talked about it a little bit last time. It'll look a lot like the previous exam. And I'll talk more about it the closer we get, but I think you get the basic idea. What else? We have to pick a day for the final. I got, since it's not we're not doing the final in the 3-hour window. I got special permission for us to have the final whenever we want to have it. We'll have both sections do it at the same day. I'll make it available. You have 24 hours, just like with the exams, and we'll have to pick a day. So maybe after we've done the second exam, at the beginning of class, we'll do a poll using the SETI interface here, and we'll see what day works best for most of you, and we'll then run with that. That's my thinking at the moment. I'll give it a little bit more thought because I've never done it this way, but it should be okay. Does anyone have any questions about anything logistical or about anything? Okay, well, let's take a look at this warm-up question. Last time we spent some time talking about how you calculate the temperature of a world. And I said it applies to anything, a planet, a moon, an asteroid, a speck of dust, can also apply to a spaceship. And there are two versions of the equation, one for worlds that distribute their temperature, or objects that distribute their temperature pretty uniformly across the surface, and ones that don't, ones that develop a hot spot facing on the sun-facing side. So here we have, that's a picture of Mercury, and that's some of my lunch that somehow got on there. But anyway, consider a manned mission to Mercury's polar cap. The polar region has nothing to do with the calculation. It's just to make this scenario a little bit more realistic. Why would we ever want to go to Mercury? It's so close to the sun and so hot. As we'll learn when we study Mercury, is in the polar regions, in the craters, there is actually water in the form of ice. And if we ever visit any place, particularly long-term, set up bases, etc., again, we're talking in the future. This is a pretty distant future, but at some point we'll probably do this. You need a water supply. So the polar caps of Mercury is a potential place that humans could eventually go and set up shop. Anyway, suppose we're on a mission to go there. By the time the spaceship makes it to Mercury, you're 0.39 astronomical units from the sun. And the problem we worked out last time, we're just 1 AU. So now we have this extra factor that you'll have to consider. So suppose your spaceship is 0.39 AU from the sun, and suppose you're heading straight to Mercury. So, pretty much facing the sun the whole time. One side of the spaceship faces the sun, one side faces away. How hot does the sun-facing side get? In kelvins. And you can assume 90% reflectivity in this problem. It's typical of metals such as aluminum, for example. So I'll give you a little bit of time to work this out. It's a, kind of a lengthy, tricky equation. So maybe 30 to 60 seconds, something. Let's say 60 seconds. Go for it. Another 20, 25 seconds. So we got a few more responses. Feel free to keep working on it and submit it when you get something. But let's take a look at some of the values. And I think this looks pretty good. Depends how okay, I see. Splitting that bin there. So it looks acceptable. There are two equations, and we see two different answers here. And in this one here at 354, that is the correct answer. I think those of you who answered the smaller value probably used the other equation. So let's start by reviewing the cases for when you use each of the two versions of the equation. So here we're talking about planets, but again, it can apply to anything. If you have a world, a planet, a moon, an object of some type where the temperature is pretty uniformly distributed, you have one equation that gives the slightly lower value. And in that case, you're calculating the average temperature of the object on the surface. And for planets anyway, you get this in one or both of two ways. If the planet's rapidly rotating, then the hot side doesn't have time to get too hot. And the cold side, the dark side, then rotates around and is heated by the hot side. So like on Earth, Earth is a rapidly rotating object. It gets warmer during the day, but not by much. It may seem like a lot to us because we're really sensitive to heat, but compared to absolute zero, the temperature during the day and at night is pretty similar. Another way that you can get a uniform temperature is if you have a thick atmosphere. And I gave Venus as a good example of this. That thick atmosphere can carry the heat from the hot area to the cold area. There's some of that going on here on Earth as well, though our atmosphere is relatively thin. It's mostly the rotation that keeps a uniform temperature. And if you have neither of those, if you have a slowly rotating world with no atmosphere to redistribute the heat, then you won't have an average, or your average temperature won't be given by that equation, but you can use the second equation we developed with the slightly higher coefficient in front to calculate the temperature of the hot spot, the spot that's directly under the sun. And for this particular problem, we're talking about the spaceship. It's heading towards the sun, one side always facing the sun, so it will have a hot spot on the sun-facing side. Let's put up the math here. In this case, I'm asking you for the subsolar temperature, the temperature facing the sun, and it's 393 times this stuff. If it's the other case, a rapidly rotating or sufficiently atmospheric world, it's the other equation. All this stuff's the same. It's just the coefficient's different. It's, what is it, 278, something like that, I believe, as the other coefficient. Okay, this is the subsolar temperature, so that coefficient. The albedo, it's 90% reflective, so it would be 1 minus 0.9, which would be 0.1 to the quarter. And then this time, unlike last time, we also have a distance that you have to input. Last time it was 1 AU, so all this canceled, but this time the spaceship is almost there at Mercury. It's 0.39 AU from the sun, so you have 0.39 to the minus 1/2. So the biggest challenges are figuring out which equation to use, and then once you've done that, doing the calculation. And usually that means these exponents. You have to be careful when you use the caret sign to do it to the, 1/4, put that in parentheses, or negative 1/2, put that in parentheses. And you get 354 Kelvin, which if you convert to Celsius is 81 degrees Celsius, or in Fahrenheit, that's 178. So even though with this aluminum hull, which is pretty reflective, it still gets really hot on the sun-facing side, 178. You wouldn't want to touch that. But, you know, you presumably have some cooling system to redistribute the heat on the inside, or we would build a spacecraft that rotates. And that's a great way to generate an artificial sense of gravity if your spaceship is rotating. Okay, so hopefully that all makes sense. Any questions about that? Okay, so last time we used this equation, the first equation, the one with the smaller coefficient out front, to calculate, actually I want the dot cam here, the temperature that Earth should be according to the equation, and that was 254 Kelvin, you know, per the equation. And if you convert that to Celsius, I had it wrong last time. I had minus 23. It's actually minus 19 Celsius. And you convert that to Fahrenheit and you get minus 2 Fahrenheit. I had that part right at least. And as we talked about last time, that seems really cold. Earth's average temperature is probably more than minus 2 Fahrenheit. Where most of us are, we're in a kind of a mid-latitude region between the equator and the pole. Our temperature is probably pretty typical, and it's normally more than minus 2 degrees Fahrenheit. The true average temperature of Earth is about 59 degrees Fahrenheit. So our equation is off. It's an underestimate by about 60 degrees. And I said these equations could be underestimates because they don't account for what? What's missing? Anyone recall?
Greenhouse effect.
Greenhouse effect. Let's talk about that in a little bit more detail. So the equation is still useful, even if it doesn't work. We can always measure the temperature of a planet or moon or object. And if it's higher than what the equation says, then that difference is attributable to some kind of greenhouse effect. So on Earth, how does it work? Well, we have light coming in from the sun, and that light that makes it through the atmosphere will primarily be visible light, as it indicates here in this figure. Now think back to the solar spectrum. The sun is a thermal emitter, black body, about 6,000 degrees Kelvin. So here we see the shape of the black body, and here we see the visible part of the spectrum. So most of the light is coming out in the visible, but you also have some light coming off the sun in the ultraviolet and a bunch in the infrared going down to the radio. All these different types of light strike the Earth. But here's our atmospheric transparency plot. This is plotted the other way with frequency increasing. Well, I'm not sure which way that appears to you, but increasing to the left of the figure. So, you know, I have to do that mental flip. But the high energy stuff like the ultraviolet, most of the ultraviolet does not make it through the atmosphere. The ozone protects us from that. And as you go into the infrared, it's blocked as well. A little bit makes it through close to the visible band. But you really have these two windows, the optical band, the visible band. So visible light will make it through, a smattering of near infrared, then nothing again until the radio. We can kind of ignore the radio. It's a lot less emission and radio waves don't carry a lot of energy. So most of that sunlight, what makes it through is indeed visible light through that optical window. Then we have to consider the world's albedo, how much of it's reflected back into space. And from Earth, it's primarily the clouds and the polar ice caps that provide most of the reflectivity. And with Earth, 30% gets sent back into space. I mean, 70% makes it through to the surface, which is absorbed, and it warms the Earth to the temperatures we're used to. And again, here we have a series of black body curves. The sun is 6,000, so it's somewhere between this curve and this curve. But the Earth is much closer to this curve, 300 Kelvin. It's kind of room temperature. I'm looking at the numbers there, trying to do the math in my head. But yeah, now the average temperature of Earth, the true average temperature is not far from 300 Kelvin. So it's going to be some black body like this, peaked in the infrared, and it drops off well before the visible band. And it does have that tail down into the radio, but again, there's not much energy down there. Most of the energy that Earth is emitting, it's emitting in the infrared. And just like infrared had a hard time getting in, infrared will have a hard time getting out. You may remember we were talking about what causes the opaqueness of the atmosphere in these different regimes. And here in the infrared, it's a combination of water vapor in the atmosphere and carbon dioxide, largely, that blocks a lot of that infrared trying to make its way in and hence make its way out. So these will be the greenhouse gases, anything that holds the heat in, holds the infrared in. Infrared is, we interpret it as heat. And here's a list of the primary ones: water, carbon dioxide, methane, NO2, which I think is nitrous oxide. I may have the suffix oxide, I'm not sure, but NO2. And those are the primary ones. Let's put the doc cam back up for a second and list them. So water, and I talked about this last time, water is by far the most important of the greenhouse gases. But after that, at a lower level, you have CO2, you have methane, which is CH4, NO2, ... There are lots of things, but this is in order of importance. But water accounts for most of it. We should be at -2, we're at 59. That's a difference of about 60 degrees, 61 degrees Fahrenheit. And most of that is due to water vapor. And that occurs naturally. We're not adding that to the atmosphere artificially. So this is an example of a good greenhouse gas. There are good ones and there are bad ones. There's a natural balance, and then there are the ones that we put into the atmosphere, disrupting the natural balance. But water vapor, purely natural, it's good. If you lowered the temperature 60 degrees everywhere on Earth, I think I mentioned last time, there'd be 3 miles of ice here in North Carolina, in similar for most locations. And so Earth would be much, much less habitable. We probably wouldn't be here. So that's good that it's here. And you've felt this. I can't remember if I mentioned this last time, but if you go out in winter on a clear night and you can see the stars, it's pretty cold. All that heat from the day is just escaping. But if it's overcast, you have clouds everywhere, even in winter, it's a warmer night because those clouds are full of water vapor. It's a blanket. It's a blanket made of water that holds the heat in and keeps us warm. If you haven't noticed this in the past, be attentive and you'll notice it this winter. And it just shows you the power of water for holding in heat. Now, these other ones, they occur at natural levels too. We exhale carbon dioxide, and so before it's taken up by the plants, there will always be some of it there, and methane and these other things. They're natural processes that produce it, and Earth has achieved kind of a long-term balance under which life has thrived. But these have been increasing since the beginning of the Industrial Revolution. Carbon dioxide is up 35%. Methane is up 150%. NO2 here is up 15%, and so forth. There are other ones as well, but these are the most important ones. And most of that comes from the burning of fossil fuels. And this is, and you're all aware of this, right? This has been an issue your entire life, and I'm sure you've talked about it in other classes other than astronomy class, but it will be very important for understanding the other planets. And I'm not trying to be political or anything. I do have strong political opinions, but I very much dislike professors who share them to their students. So, I try to keep that to myself in class. But this is just the science, all politics aside. We're burning a lot of fossil fuels. And it's driven by population growth, by our population. Here's a plot of population over the ages. If you go back 10,000 years BC, there are about 4 million people on the planet. And then year zero, we're up to about 190 million. And here we are, you know, in the 20th century is right around here, and the numbers are still pretty low. But then, boom, it just skyrocketed. We're over or approaching 8 billion now. And so just over the course of a generation or two, we've gone from the planet being almost empty to the planet being almost full. If we stretch out that last bit here, here's the Industrial Revolution beginning around 1750 with 1 billion people on the planet. And then here around 1950, after World War II, the population just takes off. And we're kind of at the fastest rate of increase now. It won't keep increasing at this rate. It will level off because there's only so many resources, right? We have to make enough food to feed everyone, enough energy to meet everyone's needs. And so there's a limit, given current technology, what a planet like ours can support. And really, if you want to be philosophical about this is science's fault. Hopefully science also comes up with the answer, but before we had the scientific method and scientific inquiry, a lot of people died due to disease. We didn't have efficient ways of farming and agriculture at these tremendous scales. Science made that kind of stuff possible. We figured out ways to cure diseases so more people can live. We figured out ways to produce food at huge scales and other necessities at huge scales so we could support more people. So because of scientific advancement, it made this possible. But at the same time, all these people require energy. And the primary source of energy right now is burning fossil fuels. And this isn't like the ozone problem that we talked about last time. That problem, it's driven by CFCs, which impacted just a small sector of the economy. Like dry cleaners had to come up with other ways to do their dry cleaning. And that's too bad for them. They had to pay a little bit more money, but through legislation, international action, we were able to change that. This one's harder because the economy is mostly driven by fossil fuels. We can't just stop using them overnight civilization would collapse. But we got to find ways to switch because this is being driven very, very quickly. Over the past 30 years, this kind of temperature change has increased the temperature by about a degree over approximately the past 30 years, maybe about a degree and a half since the beginning of the Industrial Revolution. Most of it's been fairly recently. And you go another 30 years and there's another degree, and another 30 years, another degree. And we're not talking 60 degrees. We're not talking 3 miles of ice, that kind of effect, or melting of 3 miles of ice, but adding a degree and then another degree and another degree over the time scale of a human lifespan, that will have real impacts on the climate. And I used to give a full lecture on what these impacts are. It's kind of fun and scary to think about all this stuff. But usually I'd run out of time by the end of the course. So if I have time at the end of the course, I'll dig out my old lecture and we'll have a lecture on climate, the impacts of climate change. But if I were to just hit a few basics, this figure kind of summarizes some of it. So the ice caps, the way the circulation patterns work is as the temperature increases, most of that is funneled to the polar regions. The equator may go up a fraction of a degree by the end of the century, but the polar regions could go up 10 degrees. Most of that extra heat ends up there, melts the ice caps. And here you can see the difference just between 1984 and 2016. Taken same time of year, the ice caps grow and shrink over the course of the year with the seasonal temperature variation. But you can see the ice cap's already much smaller area-wise, but also much thinner, which you can't see in a diagram like this. And this is, they looked at lots of satellite footage and removed the clouds and made this kind of composite. So you can see this. And probably in another decade or two, It's already during summer, it's pretty much open up there. New shipping lanes and stuff like that, which is kind of interesting. But there are lots of bad things. This is one of our sources of albedo, one of our big sources of albedo. You get rid of the ice caps and that energy doesn't reflect into space. It just goes into the water and heats it even faster. So it's kind of a runaway process. Once the ice caps start melting, it runs away. And that has all sorts of bad problems like rising sea levels, and a lot of our population centers are on the water. But there are other, even scarier possibilities. Up in the polar regions, the ground has a lot of frozen ice in it. We call it permafrost. And trapped in that permafrost is a lot of methane. And so as these regions warm up and the permafrost melts, we could double the amount of methane out there. And although that's only third on our list, methane, it's really potent on a per molecule basis. And so there are all sorts of just bad things that can happen. More fires, greater possibility to spread diseases. Different vectors for disease emerge with longer warm seasons, and on and on and on. So just a degree or two over this short of a time scale makes a big difference. It's problematic. Something else I can say here is if we were to somehow magically stop producing the methane and the NO2, fortunately with the water, I think I've said this, but the water, that's gone up 0%. Burning fossil fuels doesn't put more water in the atmosphere. Thank goodness, because that would be the most dangerous one by far. And plus the atmosphere saturates, it would just rain back out. But if we were to stop making the methane, the NO2, this other stuff, it would be like the ozone hole. It would heal itself up over the time scale of decades or a century. It's the time it takes for the existing excesses to work their way back out, recombine with other things. The problem, even though methane is more potent per molecule than CO2, the problem with the CO2, other than there's a ton of it that we've put up there, is it doesn't leave the atmosphere. It can cycle through the oceans and come back out, but it takes thousands of years to get rid of the CO2. So even if we fix our problems overnight, there's no getting rid of that CO2. We have to come up with ways to scrub it out of the atmosphere. And there are ideas, but there's just no technology that can do it on a global scale. That's like distant science fiction. So whatever we do now, we're kind of stuck with there. Anyway, that's kind of my 10 cents on climate change. It's not often in an astronomy course you can spend time talking about something that actually matters. So I like to spend a little bit of time on it. Now pause for a second and see if there are any questions I can answer. I'm not an expert, but I read like everybody else, and maybe I can answer a question or two if you have any. You're my quiet class, so it's like pulling teeth. The other class, I can't get them to shut up, and I'm always like falling behind, but okay, we'll stay ahead then. Again, if we have time at the end of the semester, I'll come back to it. Okay, well, on to things that don't matter. We're going to talk about the moon next. So yeah, I think that was it for climate change. Again, I'm not trying to be political here. That's just the science. The scientists don't disagree about this. And there are a few under the employ of the fossil fuel industry that disagree, but the real scientific community, they haven't disagreed about this stuff since the 70s. It's just often the politicians are slow to adopt the science. The same with smoking, right? We knew all the way back in the 50s it causes cancer and warned everyone, but no one took it seriously. Even when I was your age, is presented in the news as like a 50-50 proposition. They put both sides on TV, and just because there are two sides to a debate doesn't mean they're equal. And climate change really is the same thing. The science is rock solid. CO2, it's just a molecule. It's a simple molecule. We can measure how it retains heat. We can do it in simple laboratory experiments, and we know roughly how much we put up from the burning of fossil fuels. So it's not surprising that the temperature is going up. Okay, enough of that, on to the moon. Get the dot cam up. Now, excuse me, whenever we tackle a new world, I want to start with kind of its bulk properties, in particular its mass and its radius. And we learned back in lesson 5 how to measure these things, how to measure the mass of a world. Usually if it has a moon, you can use it, and how to measure its physical size by its angular size and its distance. So the mass and the size. It's given by M and R. And these two quantities in particular are useful because you can immediately calculate 3 other things from them. All 3 of them are quite useful things. So let's see, let's start with the size. The size of the moon, and we'll do this as a ratio kind of thing because you've gotten good at doing the ratio calculations. They're really fast. So the size of the moon, let's see, I have some notes. Let me pull them up on my other screen. And I need to shrink you all so I can see them. Okay, so the size is 0.273. I don't know why I have that giant gap there. 0.273 times the radius of Earth. So a little bit over a quarter the size of Earth. And the mass is 0.0123. That's easy to remember, 0.0123 times the mass of the Earth. Okay, and so there are 3 things that we can calculate right away from this. The first is the average density, which is proportional to mass over radius cubed. We did average density calculations in lesson 5. And again, this is a ratio approach. So as long as we do it in terms of a comparison object, we don't have to worry about the constant proportionality. We can do a direct equality. And our comparison object will be the Earth. That's what that little circle with the plus sign means. Let's enter, and I'm going to go through this in full detail this time, but as we do other worlds, we'll be able to do it much more quickly because of this experience. So let's see, mass is 0.0123 divided by 0.273 cubed. And I actually didn't calculate that out, but just in words, that is the fraction of Earth's density. Whatever that number is, it's the fraction of Earth's density the moon is. Now, if you want to know the moon's density, you just then multiply it by Earth's density, which is 5520 kilograms per cubic meter. And this again is Earth's. And then you have the moon's, which turns out 3340 kilograms per cubic meter. So this fraction is probably like 60% or something. And we already learned that the density tells us a lot about composition. Earth, with that density, it's somewhere between rock and metal, so Earth is a mix of rock and metal. Here with this density, the moon, that's just a little bit above the range that we expect for rocks. Rocks should be about 2,000 to 3,000. That tells us the moon is primarily rocky, maybe with a little bit of metal mixed in. So it should have a small metal core. Okay, that's the first one.
Dr. Reichert, that first fraction was 60.4%, so you're pretty dead on.
Okay, great. You get good at being able to do math in your head. After a while, particularly astronomers working in factors of 10, we can do logarithms in our head and stuff like that too. Okay, the next one is surface gravity. This is proportional to m over r squared. So plugging the stuff in for the moon, 0.0123 divided by 0.273 squared comes out to be about 1/6. And what this is your weight multiplier. There we go, weight multiplier. Why is it m over r squared? Well, remember the gravity equation. The force of gravity is G times big M little m over r squared. And here, little m, that's you, that's your mass, and G is just a constant of nature. So it's really all about the m over r squared. And so for the moon, you plug in the values, you get 1/6. This means if you go to the moon, your weight will be 1/6. So if you're trying to lose weight, the easy way is to just go to a planet with a different gravitational field. Normally, when people say they're trying to lose weight, they're actually trying to lose mass, which is, of course, more challenging to do. I don't know. Going to the moon is pretty challenging too. So anyway, this will matter, particularly gas giants. Their upper atmospheric layers, how compressed they are, can change the appearance of the planet. And so we'll come back and use that. But the third one we'll make use of a great deal, and that is the escape speed. And this is important if you're trying to blast off of a planet and get away from it, but we'll use it more in the context of planetary atmospheres. Whether you retain or lose an atmosphere depends on the escape speed. You know, atmosphere is full of atoms. The atoms are bouncing around. If they're bouncing around sufficiently above the escape speed, it'll escape and you won't have an atmosphere. So escape speed is proportional to the square root of m over r. And you may remember back in lesson 2, it was the last bit. I think I may have assigned it by video, but we derived the escape, well, we derived the speed to go in a circle around a planet. Then I gave you the escape speed, which is similar. The escape speed is 2 times g times the mass of the planet divided by the radius from which you're trying to take off. So again, these two are constants. So the rest, square root of mass over r. If we do it in Earth units, that's the square root of 0.0123 divided by 0.273 square root. And it equals something which I'll write in words, fraction of Earth's escape speed, which you can then multiply by Earth's escape speed, which is 11.2 kilometers per second. Again, that's the value for Earth. And with the moon, you get, that is 2.4 kilometers per second. So you see with the moon, it takes much less to get off. If you think back to the Apollo missions, to get off the Earth and go to the moon, it took a Saturn V rocket, the biggest rocket we ever built. But to get off the moon, we just used a little mini booster that didn't have to achieve nearly the same speed. 11 kilometers per second. Think how long it takes to walk 11 kilometers. And then imagine traveling it in 1 second over and over. It's just crazy the speeds that we can achieve with these rockets. But you don't need to achieve nearly as much to escape the moon. And that's a big reason why the moon has no atmosphere. It is easy for the atmospheric gas to just float off into space. But we'll tackle that a little bit more carefully. I'm going to hit the focus button and give you just a second there in case you need to get any notes. And I know on these Zoom broadcasts, sometimes the resolution isn't that great, but you know, when I save it on my computer, I save it in full resolution. So if you go back and watch it on YouTube after I post it and you set the resolution to maximum, you can see it all very well. Okay. Again, we're not going to go through this much detail with every new world we come across, but we'll just kind of write out what the results are, and that would tell us some things about the world. And these are nice, simple ratio problems, so you should expect them on exams. Okay, let's see what else we have here. Okay, so our moon is kind of special. It's one of the 9 large moons of the solar system. And that makes it unusual because we're a tiny planet. We have a large moon going around a small planet. All the other moons go around the gas giants, which are huge. So there's something special going on here. Here it is to scale. We saw this before. We did a scale model of the sun, earth, moon system. And so I put this figure up then. Here's the Earth and here's the moon to scale. Again, in many of the figures we're about to look at, they won't be to scale. So just keep this in the back of your mind. Some people sometimes refer to this as a double planet, since we have such a large moon for such a small world. And it technically doesn't meet that definition. To be a double planet, it means something in particular. So here we have the Earth and the moon in orbit around the sun. The sun's off the top, and here is the elliptical orbit of the Earth-Moon system going around. We think of Earth going on an elliptical orbit, but it's actually the Earth-Moon system that does. It's our center of mass, which is the black dot. It's very close to the center of the Earth, but not exactly, because the moon's out here tugging on it, pulling it a little bit away. But it's the center of mass that orbits the sun, and Earth and moon orbit the center of mass as the center of mass orbits the sun. In the case of the Earth-Moon system, the center of mass is about 1/3 of Earth's radius from the center. So not too far, but a little bit. That means as we go around, we kind of wobble as we go around the sun, because the moon makes us do that. Now, if the center of mass were external to us, between the Earth and the moon, then we would be a double planet. And the best example of that is probably Pluto and Charon in the outer solar system. Charon's the large moon of Pluto. They're technically a double whatever. And it's not a planet. Pluto's not a planet. It's a dwarf planet, and Charon's not. It's a double world. I'm not sure what you'd call it. But here we're a traditional planet with the moon, so the center of mass is still inside of our radius. In this motion, it's analogous to throwing a wrench. I don't know if you've ever done this, but a wrench has a really heavy head, and the handle's usually made of some lightweight material like aluminum. And so when you throw it, it's the center of mass that will arc and travel down and hit the ground, marked here. And that center of mass is close to the head. So the head does a small orbit around the center of mass, where like the end of the handle does a bigger loop around it. And that's kind of how the Earth and moon are traveling around the sun. Now, the thing I want to end up with today is the formation of the moon. How did we get such a large moon? It's really unusual. And there have been 4 theories put forward over the years, 3 of which can now be ruled out. Some can be ruled out almost immediately. But I'll present all of them, and the 4th one is the one that we think is correct. I'll save that for last. But let's try to get through all of them, even if I have to go a minute or 2 over. So let's put up the dot cam, and I'll go to full size. So formation of the moon. So the first theory is called the sister theory. And the idea here is that we formed together, already orbiting one another. So we're at some distance from the sun, and gravity started pulling stuff together, and more came in and was forming the Earth. Maybe there was a disk of material orbiting the Earth, and in that disk, maybe the moon formed. Maybe we formed together at the same time, in which case we would be made of the same stuff. Same material. And this would imply that we would have the same density. If we're made of the same stuff, the moon would have as much metals and rocks as we do, but we're not. We don't have the same density as we just calculated. The density of the moon is much less. It's much more rocky, and we have more metals than the moon. So that rules out the sister theory. We didn't form together. If we did, we would be essentially the same. So if we didn't form together, maybe the moon formed someplace else and we captured it. So this is called the capture theory. And this is both, there are 2 points here. The first point is it's difficult, and the second point is it's impossible. Let me start with the difficult point first. It's very hard for a small world, meaning Earth, forget small, a low mass, very difficult for a low mass world such as Earth to capture something as high mass as the moon. The moon, it has a lot of mass, it's moving at a certain speed, has a lot of energy, and if it's not coming in at just the right angle and just the right energy, it won't enter orbit. It'll just keep going. It may be deflected, but it'll just go off into space. to capture a world as big as the moon, you need to already have a moon. You would need a small moon already. And that moon, basically, when the big moon comes in, Earth, the big moon, and this theorized small moon, they do a complicated gravitational dance, and the small moon absorbs the energy and the momentum and gets shot out and leaves the solar system. That's the only way to capture a world. And we'll see this. The large moon Triton orbiting Neptune is a captured world. It has to be. It's orbiting backwards. There's no way it would have formed that way. It had to be captured. So if this did happen, Earth would have already had to have a moon, which would have to explain that. And it would have had to be just right to capture the energy and shot out. So technically it's possible. I'll put a little grumpy signal there to indicate that it's not likely. But there's a second problem. And that second problem is we've been to the moon. We've picked up a lot of rocks, brought them back for analysis, and they're the same as the rocks here on Earth. We have the same mantle. Not just the same density, but geologically, it's gone through some kind of common process. And if the moon formed someplace else, we wouldn't have the same mantle. It would have its mantle with its composition and its geology, and we would have a different one. The fact that we have the same mantle says that no, it's not captured. So we have a quandary. It didn't form with us and it didn't form without us. So we got to be a little bit more creative in our thinking here. Another theory came up called the sister theory. It's really kind of creative, but it doesn't work. The idea is, what if the early Earth was molten and it's spinning? What if it was spinning super fast? If it's spinning super fast, it would get elongated. And if
I
it's
have a quick
fast,
question.
yeah, go ahead.
Does that mean that there's two sister theories?
Oh, my bad. My bad. Thank you. This is the daughter theory. Sorry, not the sister theory, the daughter theory. In other words, the idea is the moon is birthed from the mantle of Earth. So imagine a molten Earth spinning so fast that it stretches out and a blob breaks off. That blob would be made of mantle material. So you'd have a moon made of Earth's mantle. It'd be great. It would explain everything. Two problems, though. The first problem with the daughter theory is Earth would have to be spinning way too fast. Like, it would spin every couple minutes, and it would still be spinning on its axis every couple minutes. A day would only be a few minutes long. You got to spin it that fast to break off a blob, and that's not the case. And secondly, that blob would break off with a speed greater than the escape speed. So it wouldn't stay in orbit. It would go off and probably leave the solar system. So you could create a moon this way, but it wouldn't still be here. So it was a nifty idea, but it just doesn't work out physically. Which leaves us with the last idea. I'll just write it here. It's called the impact theory. And I'll end with a slide or two about that. So here's the idea behind the impact theory. At first it seems crazy, but as we go from world to world in the solar system, we're going to see this happen over and over again. Almost every planet suffered a major collision. It seems the early solar system probably formed twice as many planets, and they gravitationally pulled themselves towards each other and had major impacts. So we've run this through supercomputers, and the most likely explanation is something about the size of Mars. Not Mars, but something about that size. They've given it a name, Theia, this world that existed 4.5 billion years ago, might have existed, probably. And it strikes the Earth. And here you can see this is what the Earth would look like at 4 minutes, at 8 minutes, and at 2 hours. It would split us wide open. And don't be fooled by the blue. There's no water. At this point in time, we're both just molten balls, not even differentiate. Well, we are partially differentiated at this point. But we would reform, but some material would be thrown out, and that'd be mostly mantle material. It's the mantles that get most of the blow, absorb most of the energy. But since it's an impacted, the planet absorbs a lot of the energy. So what's thrown off is thrown off less than the escape speed. Most of it is less than the escape speed in its mantle material. So it'd pull itself together into a moon, or maybe a couple moons that eventually merge into a single moon. It wasn't traveling so fast that it would escape, so it stays in orbit, and you end up with a moon made of Earth's mantle. That explains the difference in density, but the same geological compositions for the surface material. It also, as a freebie, explains Earth's tilt. Earth is tipped 23.5 degrees, would never have formed this way. And once you have a large moon, it holds that tilt in place. So that can explain why we're tipped over as well. And here you can see another numerical simulation where the cores of the two worlds are in blue and the mantles are in red. And again, the mantle absorbs most of the blow and is thrown off with the highest speed. The core material, that's the next to hit, and it's thrown off with the lesser speed, and most of the core material comes back and merges with Earth. And it would differentiate, and so the core down at the Earth is probably a mixture of Earth's original core and Thea's core. And our mantle's mixed as well, both here on Earth and out in this object that became the moon. So I'll just end with this. Well, it's not a picture, obviously. No one was there to take a picture, but an artist's rendering. I like this. Whenever I'm having a bad day, I like to look at this. Because if you think you're having a bad day, you're not. This is a bad day. So anyway, we'll continue next time with the moon's interior and why it doesn't have an atmosphere. Okay, thanks a lot.
Thank you.
Thank you.
My pleasure.
Thank you.
Thank you.
Thank you, Dr. Eikert.
My pleasure.
Thank you.